right, good morning, everyone. I want to start off by correcting a mistake I made yesterday on the limits and continuity worksheet. It's that very last problem that we did with IVT. I misread the problem, so I want to kind of make sure that I can clear that up. We talked about how IVT, this is on the back page of yesterday's notes. Okay, we talked about how IVT is where we can guarantee all the y values that sit between the endpoints. And I said that both C and D look like they're IVT, but look like C was more generalized, like it's identifying every y value that sits between -3 and 6. But a student pointed out that this is probably more likely talking about the fact that I was reading it as it's possible that every y value between -1 and 3 is hits between my graph. But I think this is more saying that only y values between -1 and 3 is reached between -3 and 6. And if we look at it that way, then that's not necessarily true, because the graph could look like this, right? It's true that every y value between my endpoints has to be hit, but it's not restricted to just those y values, right? The graph can easily dip above and below. So I think looking at it from that lens, I think C is not going to be correct. Okay. D is going to be the better answer because it's saying that we can guarantee a y value of 1 for at least one value between -3 and 6. And that's true because I have one endpoint sitting at -1. I have another endpoint sitting at 3. And those are y values that are clearly above and below my target y value of 1. So I misread the problem choice for C, and I think D is going to be the better answer for IVT. Okay, does that make sense? Any questions with that one? Okay, all right, so let's move into our derivative worksheet. Okay, so today we're going to talk about derivative rules. We'll talk about general rules, especially with expressions that are related to one another by one of these operations, either by multiplication, which we use product rule. If two expressions are related to one another by division, we got to go through quotient rule for its derivative. If one function is within the other, we got to go through chain rule. And if I have something that is not quite a function, but still a smooth curve, if it doesn't pass a vertical line test, we can still find the derivative using implicit differentiation. And then we may not get to this today, but derivative of inverse at a point. Okay, so this is more like chapter 5 material, but I just merged some of the chapter 5 and 2 together since they're all kind of involving with derivatives. Okay. So I hope that most of you are considering choosing that AP exam in May. I know that one concern that I've mentioned before is, what about all these rules I need to memorize? But I think truthfully, most of the rules that's going to show up on the AP exam, I think you already know pretty well because you've seen it so many times. And there are more derivative rules than these 8 that you see, but these are the ones that show up over and over again. I think it's possible for the more obscure ones, those are fair game to show up, but I mean, over these past years, I just haven't seen it, if any at all. So if you just focus yourself on knowing these rules, then I think chances are you're going to be covered in terms of rules you need to memorize, at least from a derivative standpoint. So you definitely need to know power rule, right? That's guaranteed to show up. E to the u and natural log of u, those are very common as well. But chances are you're not going to see like a to the u or log base a of u. Those are pretty rare. Or I don't know if I've seen it. Maybe a to the u, but I don't think I've seen log base a of u recently. Sine and cosine, those are very popular derivative rules that we definitely need to know. Tangent and secant, those show up as well, even though these are less common, but I've seen these show up. If there's an arctrig that shows up, it's usually just arctangent. And that's nice because arctangent is the easiest, the cleanest one of the arctrig rules. Like there's no square root involved like arcsine or arcsecant. So yeah, if you know those 8 rules, I think you have everything covered, most if not all covered, amongst ones that could show up on the AP exam. But we definitely need to know these rules like product, quotient, and chain. But we've seen it so many times. Even if you've forgotten a little bit of it, you're not starting from scratch, so it won't take much effort to commit those to memory, especially after we practice today. Chain rule, just as a reminder, this is a composite function, so there's an inside and outside portion. We take the outside's derivative followed by the inside's derivative, but we place them not inside one another, but we place them next to each other, right? So they're outside of each other, and we'll practice with a little bit of chain rule. Okay. Now, power rule is going to be the one that you use the most often. That's going to be the one that shows up the most, but it's also the one that is easiest to make mistakes with. So I want to make sure I go through, review with you the power rule conditions. Okay, so first is we need to convert radicals to rationals too, so we can see what exponent we're working with, so we know what to bring down, so we know what to subtract or subtract from. Second, make sure that your variable is sitting in the numerator. If your variable is in the denominator, and if you try to do power rule, you may think that you're doing power rule, but it's not going to be in the right place, so your exponent is off, and it's not going to produce the right derivative for you. Parentheses. If you see parentheses, we have to look for ways to resolve them. Sometimes you're stuck in a situation where you can't resolve the parentheses because order of operations prevents you from being able to do that. If that's the case, then power rule is probably not the method we need to explore. Maybe it's going to be a chain rule problem. Okay. And if we have fractional terms, we need to resolve that as well. So if I have multiple terms with x or one term in the denominator, I like to split up into individual fractions and then handle them accordingly and do power rule cleanup within each individual term. Okay, so number one, let's start with this first one here. Find the derivative of this function. And I have all these different types of problems mixed together. I have e to the x, I have natural log. But these are all nicely separated, so we can treat each like its individual term. No need for product, quotient, or chain, or well, maybe a little bit of chain, but no product and quotient here. But the last few terms, though, will require a little bit of cleanup. So I'm just going to rewrite the terms that are already set to go. So my first few terms, no adjustments necessary. But when I reach that 3 over x squared, how would you rewrite that?
X to the negative.
Good, yeah. So we got to bring that x up to the top. Because that x squared in the denominator is out of place, at least for us wanting to apply power rule. And then square root of x to the 5th can be rewritten as
X to the 5 over 2.
Yeah, 5 over 2. I think this is the one that gives students the most trouble. I think a lot of students interpret that space as a 1, but it's actually a 2, right? Square root is actually a 2. And we don't put it as 2 over 5, we put it as 5 over 2. Okay, every term is set up and ready. I can apply the appropriate derivative rules for each term. Okay, so one term at a time, 3x squared becomes, yeah, power rule. E to the 2x becomes, good, yeah. The order, I normally start off with that u prime after, and then after I realize, oh, okay, I can move it to the front, then I move to the front. But if you do it all in one step, no problems there either. But I'll just follow the rule and say e to the u times u prime. Yeah, a little bit of chain rule there. Okay, how about natural log of 4 minus x? Good, so we take what's inside the parentheses, we take that derivative, that becomes -1, and then we keep the original expression inside the parentheses. Notice your derivative doesn't have natural log in it. I think sometimes students, they still include natural log in their derivative, but in this case, right, our u value doesn't have natural log in it, so it's not going to show up in the derivative. Okay, power rule, next term. 3x to the -2 becomes to the negative. Good, right, so we subtract 1, so it's going to go even further into a negative number, okay? All right, power rule again, 5 halves x. What's my new exponent going to be after I subtract 1? Good, so I like to put a 2 over 2 there just as a visual reminder that I'm subtracting with common denominators in place. And then plus, what happens to the 3? 0. Okay, you don't have to put +0. I'm just putting +0 to indicate that, yes, we did take care of that constant, but you can just completely just have it, you know, have an empty space there. All right, we have our derivative. I'm just going to do a little bit of cleanup. Any questions with one? All right, number 2. I see a radical there, so maybe there's something that I can do to rewrite it. What could we do to rewrite this?
Parentheses to the 1/3.
Yes, the 1/3. U substitution is for integrals, but we have something on the derivative side of things, which is chain rule, right? But yeah, U substitution is the integral version of chain rule. But yeah, first, you're right. We're going to rewrite that parentheses to the 1/3. So I'll indicate the need for chain rule here. And we know we need chain rule because we can't distribute that through, right? We can't rely on power rule. Order of operation prevents us from being able to have that in a different form. It's kind of stuck in that form. So we look at this as, well, maybe I can handle this using chain rule. If I can identify outside and inside portion of my expression, I can split up using using composite functions for chain rule. Okay, so what's the outside portion of my expression here?
1/3.
Yeah, that parentheses to the 1/3. I will treat the parentheses as its own variable, and then when it's time, I'll just do power rule for that portion. Okay, the inside portion is what you see inside the parentheses. And we're just going to take turns with each of their derivatives, and we're just going to follow through with chain rule. So outside's derivative first, keep the inside intact. Okay, so what's outside's derivative? 1/3 parentheses, subtract 1 times
Negative 6x.
Yeah, negative 6x. I think a common mistake I see is sometimes students, they want to put that negative 6x in this space, but this space is reserved for the original expression. So if you look at this, this matches nicely with chain rule that's defined here. F prime of g of x, that's that 1/3 parentheses of negative 2/3. G of x is the original inside portion times inside's derivative. So we're just following what the rule is spelling out for us. Okay, we can do a little bit of cleanup. I'm going to merge the coefficients together, and I'm going to push the negative exponent down to the denominator. You can either leave it like this, or you can reduce. You can even convert it back to a radical. That's acceptable as well. I'll say or because either form is fine. And I want to kind of give you a lot of varieties of answers because I want you guys to be able to recognize the different forms in case on the multiple choice exam you get to the answer that is correct, but that form doesn't show up in your answer choices. You need to kind of play with the different forms to get it to match with whatever form is presented in your answer choice. Yeah.
So let's say we leave it as 1/3 5 minus 3x squared to the negative 2/3 times negative 6x. Would that still be acceptable in the AP exam?
I think so. Yeah. Yeah, I don't think there's. For me, I like to have students bring it down for positive exponents, but I don't think you'll lose points on free response. But chances are this will show up on the multiple choice, so your answer choice will look probably more like that. Yeah. But yeah, College Board is very lenient about unreduced forms. They're not going to take points off if your answer is equivalent to a cleaned up version. Okay, any questions so far? All right, number 3. We have a function. We're asked to find the equation of the tangent line at x equals 1. So tangent line equation, we need to find order pair, we need to find slope, and then dump it into the point slope form, right? So I'm going to just identify the need for those information. So to find, I'm going to start off with my point. That's the easy part. I'm just going to take 1 and put it into my function, get my order pair. Negative 2 over 1, which is negative 2. So that's my order pair. To find slope, I need to get to the derivative and then plug in the value into the derivative. But to find the derivative, what's involved here? Yeah, this is quotient rule. We need to recognize the need for quotient rule here. Okay, so let's practice that. Quotient rule is spelled out up here. Okay. f prime 1 times, oh, and then the f is the top portion, and I'm treating g as the bottom portion here. The original g function, no changes, minus f, and then g prime, all over my denominator, original denominator squared. Okay, so with quotient rule, I typically like to clean up the numerator, but leave the denominator alone. There's no need to expand that out. I think that factor form is perfect the way it is. And also careful, right? We don't want to reduce when we're not in a place that doesn't allow for us to do it. We can never do this, right? So a lot of students, they want to cancel the 2 minus x squared, but this 2 minus x squared is attached to the minus sign. We can't cancel across addition or subtraction, so this has to stay. So we're going to just combine like terms as best we can. Okay, if I just think of this negative 2x, I'm going to move it to the front and just think of it as, well, the two negatives become positive. I'll just distribute the positive 2x through the x minus 3. And I'm just going to clean up the numerator a little bit more here. Okay, so here's my f prime. Denominator, I'll leave it in parentheses. All right, so there's my cleaned up version of the derivative. And now I'm just going to find the slope. Find f prime of 1. So negative 5 plus 2 is negative 3 over 1, which is negative 3. Okay, so there's my slope. Okay, there's my point, there's my slope, point slope form. Leave it in point slope form. I mean, you can go to slope intercept form, but you know, why continue working on the problem if it's already correct? All right, questions so far? All right, look at number 4. We're also asked to find the derivative here. Anything that stands out? Is there a special process we have to involve here for number 4? Yeah, this is product rule. All right, we need to understand that x squared and sine 2x are distinctly separate terms, and they're being multiplied. So we can't just find each of their derivatives and be done with it. We have to involve that product rule because they're connected through multiplication. Okay, f prime g plus f g prime. Okay, f prime 2x. Keep the original g function. Back to the original f function. Okay, what's sine 2x's derivative?
Would be just cosine.
Close.
Or would it be 2 cosine?
Yeah, that's right. Yeah, so we have Cosine of sine u becomes cosine of u times u prime. We got to take care of that slight chain rule because of that inside portion 2x there. Okay, not much to clean up. Sometimes you may also see an answer choice where they're factoring out the 2x. Just x. Okay, back page. Okay. Okay, so now we're moving into implicit differentiation. Now we're moving away from functions into equations that look a little messier because of the fact that the y's are not going to be separated easily from the rest of the x's, which means that it's not going to pass a vertical line test. It may be a strange looking curve, but we can still find a slope formula for that curve. We just have to keep track of these multiple or these y's that are not easily separated by itself. So what we do is we first start by taking the derivative of a term with y in it. But sorry, if we take a derivative of a term with a y in it, we're going to apply whatever derivative rule is necessary for it. And then immediately we're going to attach a times dy dx. So if you see 3y squared, you'll make it 6y because that's power rule for that term. And then you would multiply by dy dx. So after all that is taken care of, you may have multiple dy dx's kind of just spread out all over your derivative equation. And then the next step is just rearrange them. Because you're done with the calculus, you're just going to rearrange the terms until all the dy dx terms are on the same side. I say the left side because that's just my habit. But either way, I just want the terms that have dy dx's gathered together on one side and all the non-dy dx terms on the other side. That way I can factor that dy dx variable out and I can solve for dy dx. Okay, so let's practice that process for number 5. We have an equation for number 5 here. This is not a function because you see y's kind of mixed into the equation here. But we can still just jump into the derivative process. Okay, so every term is nicely separated. I think power rule can handle each term. So x squared becomes what? 2x. Right? Nothing unique, nothing special with that. So we move on. Y squared becomes y and dy dx, right? Because we're saying I'm finding the derivative of y with respect to my independent variable x. So I need to include that notation. Oops, dy dx equals. Good. The 5 goes away to 0. And then y's derivative is 1, just like if it was x. Right? If it was x, you will make it 1. For y, you'll make it 1 as well. But even though the y disappears, we are asking for y's derivative, so we need to include that dy dx. I think that 1 is helpful because when you do factor that dy dx out, there's a visual reminder that there's something left over, that we don't just want to wipe out that. There's a placeholder for that term. Okay, so we're done with the calculus. Now we're just going to rearrange, put the dy dx on the same side, and then separate it from that 2x that doesn't have dy dx in it. Okay, we factor that dy dx out. And then finally, we divide over. Okay, any questions? So I want to point out that this may look a little different than other f primes we've seen in the past, but it serves the same purpose as all those f primes. All it does is it's just describing the slope behavior of the original graph. So even though you may have something strange like a y in its derivative, if I give it an ordered pair, in return, it's going to give me the slope value just like with other derivatives. So if I extended this problem a little bit here, let's say part B says find the slope at order pair 2, 1, for instance. I'm just making up an order pair here. Then you simply have to take that order pair, dump it into the derivative, and in return, whatever number you get back, you know that's the slope. So typically the notation is a vertical line with an order pair next to it to indicate that I'm having to involve both my x and y value into my derivative, into my slope evaluation. So if you want to find the slope of if you want to find equation of tangent line, you can also go through it using something that involves implicit, right? You take your order pair, you take your slope, and then do point slope form after that. Okay, any questions with 5? Okay, number 6. What do you guys notice?
There's a product rule.
Yeah, good. So that first off, similar to number 5, right? There's a need for implicit because you see y's kind of within the equation, kind of mixed together with the x's. But the thing that's hard to spot is that middle term, right? That middle term is easy to overlook, but there is a product rule hidden in that process. Right? We don't see parentheses, but we do see x and y, and those are obviously different terms that cannot be merged together. They have to stay separated, and they're being multiplied together. Right? So we have to go through product rule there. Right, so that's easy to miss, so I want to make sure that we take the time to understand what that looks like in terms of product rule for implicit. Okay, so I'll indicate that here. Okay, but the other terms are just standalone, so I'm just going to jump directly into each derivative, and then we'll handle that middle term when we get to it. 3x squared becomes 6x minus, I'm going to leave a big space here for product rule that I'm anticipating to use. I'll treat the 2x like my f, and then I'll treat the y as the g function. Okay, so f prime, what's f prime going to be? Just 2, right? The original g function, no changes. I'm just going to bring down the y. Back to f. And what's g prime?
1 dy.
Good, 1 dy dx. I'll just put dy dx here. All right, so we're done with product rule for that middle section. Okay, next term, 5y squared. Yeah, 10y and then dy dx. Okay. Equals, good, 0. I think sometimes when we see a constant by itself, we typically think that it's not affected by the derivative. And sometimes I see students leave that constant there. But just remember, every term is being impacted by the derivative, so that 1 is going to turn into a 0. Okay, we're done with the calculus. The rest is just cleanup. Any questions so far? Okay, all right. Here's our cleanup stage. Distribute the negative through. I'm going to keep my dy dx terms on the left. I'm going to move my non-dy dx terms to the right. Okay, let's factor that dy dx out. Divide the parentheses over. Okay, that's fine, or you can factor 2 out and then reduce even further. Yeah, either is fine. Okay, questions? Okay, all right, let's do one more, number 7. Find dy dx if y equals tangent cubed of 3x squared. All right. Anything special with this problem?
It's a chain rule.
It's a chain rule. The reason why I brought this up specifically is because these are the most intense chain rule problems, because usually we think of chain rule as just outside versus inside. Here, with trig functions, where you're going to have an outside, inside, and inner, there's 3 different parts we got to keep track of. And I think those are the ones that are the most intense of our chain rule procedures. So yeah, definitely need for chain rule. Now, there's something about this form that makes it difficult to see all those parts. So what can we do to make it easier to see all the different layers within this chain rule?
Just move the cube.
Yeah, let's move that cube. We're not changing anything, but we are making it visually easier for identifying the different parts of this what we need for chain rule. So whenever I see that exponent that's written in that form, I'm going to push it out to make it easier to evaluate. So I'm going to use bracket to differentiate from the parentheses here. So I think this is more helpful, right? Because you can just think of it as, okay, there's a bracket, there's a trig, and there's a parentheses, and that's going to that's going to help me identify the different parts of my function. Okay, what's the outermost portion that you see? Yeah, just the bracket cubed, right? And that will treat the bracket like its own variable. We'll just do power rule when we get to it. Next is just tangent. I'm going to do tangent parentheses just to indicate that, okay, I'm just going to take that derivative. And then finally, I got the 3x squared. Okay, so we're going to take turns with each derivative, and they're all going to occupy their own space. I think sometimes I see students, they want to merge all the derivatives all into one compact expression, but it's going to be all kind of sprawled out. Okay, y prime. Okay. Bracket cubed first. What do we get there? Squared. Okay. So we took care of that derivative. That's done. Next up is tangent. Tangent's derivative is secant squared. Parentheses. And then finally, innermost function, that becomes 6x. And all along the way, we're just going to insert what was there initially. Okay, so these are just occupied with the term from the original problem. That's going to just come down. Okay, any questions with that process? Yeah, so these are, understandably, these are the chain rules that students can have the most trouble with, just because recognizing the need for that third layer, sometimes it's hard to see. Okay, do a little bit of cleanup. Gonna push the coefficients together, so the 3 and the 6x. And I'm gonna bring this back into the shorthand form, that 2. So this top form is fine, but if this is a multiple choice question, your answer choice will look like this. It'll bring that exponent back into the shorthand form. Okay, any questions here? Okay, the other classes I was only able to get to number 7, so I'll stop here, but tomorrow we'll do a little bit more chain rule in terms of the notation that we got to get used to. And we didn't get to the derivative inverse at a point. That's from chapter 5, but I'll go through that. And then I have a worksheet tomorrow, which is with related rates, applications of derivatives. So we'll do related rates. We'll do some more theorems, like EVT, mean value theorem, Rolle's theorem. Okay, but I encourage you guys to start on your homework. Your homework is the other handout that you guys got. And if you're online, you can see that worksheet clearly labeled under today's date on the AP review page. I'm going to put the first and second assignments ready for you on Teams. So if you're done with it, you start uploading your assignments. So you just get that out of the way, and that way when Monday comes, you're not scrambling to try to get all your assignments in. Okay. All right, any questions? All right, thanks everyone. Hope you guys have a great day. I will see you tomorrow.